So you have, okay, very good. Okay. Thank you, Bappa. Okay. Okay. So suppose we have a chart phi equal to x1 to xn on an open set U in a manifold M taking values in Rn. So then we saw if I take any point P in U, then the derivations del del xi at P, these form a basis of the tangent space TPM. So now if I look at the coordinate functions xi, these are functions, real valued functions from U to R. So their derivatives dxi at P, these will be linear maps from TPM to R, right? And the linear map is what? Elements of TPM are derivations. They act on functions, germs of functions near P. And so L here, a derivation L will map to L of xi, right? This is how the derivative of a function on a manifold was defined. And so therefore, if I apply my dxi's, these linear maps to the tangent vectors del del xj, what happens? By definition, this will be del del xj acting on xi, right? And that we obviously is delta ij, right? The Kronecker delta. Yes? Okay. So what does that mean? That means the dxi's at P, these are linear functionals on the tangent space. So they're elements of the dual space to the tangent space, what's called the cotangent space. So that's denoted TP star M. And so what you see from this is that dxi is the dual basis of del del xi, right? Is this clear? Yes?
Yes. Yes. Yes, sir.
Right? This is the dual. So dxi is the dual basis of del del xi. Okay. All right. And now we can give a manifold structure to the tangent bundle Tm. So the tangent bundle Tm is defined to be the disjoint union of all the tangent spaces, TPM. All right. Okay. So how do we give? So I want to define charts on Tm. So the charts will come as follows. So let me take the same open set U where my chart phi on M was defined. And let me look at TU, the tangent bundle of U, which is the disjoint union of the tangent spaces at points of U. All right. Okay. So then actually our chart phi on M, it leads to a natural chart capital phi on TU. So capital phi will be a map, a pair phi comma d phi. And this will map from TU to phi u cross Rn. So phi u is an open subset of Rn, and cross Rn, this becomes an open subset of R2n. Okay. And what is the map, capital phi? Well, you take elements of TU are tangent vectors V belonging to points P, belonging to tangent spaces TPM at points P of U. So any V in TPM, you map it to what? The first coordinate will be phi of P, and the second coordinate will be d phi P acting on V, right? So d phi P, remember, is a linear map from TPM to Rn. So this will be a vector in Rn, the second coordinate. And so it's easy to see that this is a bijection. Is that clear?
Yes.
Yes, is it clear to everyone that this is a bijection? Because phi is a bijection from U to phi of U. And for every P in U, d phi P is a bijection from TPM to Rn, right? So actually, here TU is a disjoint union of tangent spaces. Each tangent space maps, in fact, linearly to a point cross Rn here on the right hand side, right? TPM maps to phi p singleton phi p cross Rn. Is that clear bijectively? Yes.
Yes, sir.
Okay. So this gives us a bijection, and using these we want to define not only a topology on TM, but also a manifold structure. I want to say that these are charts on TM. These maps phi, capital Phi, are charts on TM. Okay. So first, let me say what will the topology be on TM. So using this map, capital Phi, I can give a topology on TM. So any vector V in TM belongs to some TPM, and P belongs to some chart U. So I have some chart little phi, which gives me a map capital Phi. Now, capital Phi maps TU to an open set in R2N. So what I will say is, I look at the image of V under capital Phi, right? So that's phi P comma d phi P V. Now I take this point in R2N and I take an open neighborhood of it in R2N. All right. Then I take the inverse image of that open set in R2N, that neighborhood of this point in R2N under my bijection Phi, and I declare that to be a neighborhood of V in TM. All right. So this will give me a basis of neighborhoods of any point in TM. And therefore, I will get a topology on TM. Okay. Now, what we need to check is if instead of the chart little phi, I took another chart psi, little psi on M, then the topology that I get is the same, right? So I get an equivalent system of neighborhoods. So we will do that by checking that the change of charts. So little psi will give me a map capital Psi, right? Like just the way that little phi gave me a map capital Phi, little psi will give me a map capital Psi. And what I want to check is that the change of charts is between capital Psi and capital Phi is C infinity. All right. So, so let me look at little psi. So then let f, little f be the change of charts, psi composed phi inverse. So this goes from phi u in Rn, open subset in Rn, to psi u, open subset of Rn. This is a smooth diffeomorphism. So then psi I can write as f composed with phi. So therefore, if I let capital psi be the pair psi comma d psi, this is my other chart on TU. Then capital psi, well, the first coordinate psi is f composed phi. And by the chain rule, the second coordinate d psi is df composed with d phi, right? Yes, by the chain rule, which we saw last time. So therefore, this I can write as capital F composed with capital Phi, where capital F is the pair little f comma df. So what is this map? This goes from phi u cross Rn to psi u cross Rn. And it's the map which takes a point little x and a vector w to the pair point fx comma the vector dfx of w. All right, so since f is a diffeomorphism, smooth, so this map is C infinity. Is this clear? Yes. And so
Yes.
therefore, capital psi is equal to capital F composed with capital phi. That means that capital psi composed with capital phi inverse is equal to capital F. All right. And so this is C infinity. And so therefore Tm becomes a 2n dimensional manifold, right? Because my charts take values in R2n. All right. Is this clear?
Yes, sir.
Yes. So, I mean, the picture to have in mind is sort of you have M here, and then you have over each point of M, you have the tangent space sitting. And so the 2n dimensions, you have n dimensions from the base. You can think of it as sort of a horizontal direction. The base is m, and you have n dimensions coming from what's called the fiber. The fiber means the space which is above each point below the tangent space. All right, so n plus n is how much? 2n, right? So that's why you get a 2n dimensional manifold. So the base tells you, in a sense, if I look at a tangent vector, so this is a picture we'll be thinking about in more detail later in the course. Okay, so if I think of a tangent vector, you can think of it as having, in a sense, the base point. You can think of it as the foot of the tangent vector, and there's a head also. Okay, so the foot has n degrees of freedom, and the head has n degrees of freedom, right? So I can move the foot in this direction, and I can move the head in this direction. So the foot moves and the head moves. All right. So I'll make this more precise later. We'll understand exactly how the foot and the head move when we look at Riemannian manifolds. But intuitively, do you get the picture? Yes.
Sir, are you trying to motivate the fibers? I mean,
Yes. So this is a tangent vector, right? And this is another tangent vector. So the foot is the base point, which tangent space the tangent vector is based at. And what the head is a bit abstract. I'll have to get to it when we talk about Riemannian manifolds. But intuitively, you get an idea, right?
yes, but
Yes.
I don't get why are you moving the foot?
Well, because how do tangent vectors move? Because they can move in two directions, right? You
Yes,
can
yes,
change
they
the
can move
base
in two
point.
directions. Yeah, and
You can change the base point, and within the tangent space, you can change the vector, right?
yes, yes, yes,
So if I take a V in TPM, how do I deform or change V? This can go to some W in TQM.
yeah,
Right?
yes,
And so in a sense, once I choose what are my coordinates on the tangent bundle, so if phi was x1 to xn, then what are my local coordinates on the tangent bundle? They are x1 to xn, comma, dx1 to dxn, right? This was how I define my chart capital phi. Is this clear? Yes,
yes,
these are the coordinates on my local coordinates. So I have 2n local coordinates. So this part x1 to xn gives me the location of the foot. And this part dx1 to dxn gives me the location of the head. Do you understand now?
Yes.
Yes. So
Sir?
V would be, let's say, summation AI del xi at P. Now this changes to some W equal to summation Bi del xi at Q, right? So two things have changed now. So P has changed to Q. So this is a change in the foot, and the vector AI, this describes the head. This has changed to the vector Bi. Okay, so this is again foot, and this is head. All right. Yes, question?
Yes, sir. I have a question.
Yes.
Hello. M cross Rn is topologically different from Tm?
Yes, yes, yes.
Acha.
Locally, it's the same.
Yeah, locally it's the same, but yeah.
Locally, it is the same, right?
Mhm.
Because locally, it's Tu is identified with phi u cross Rn, and phi is the same. Phi u is the same as u topologically. So Tu is identified with u cross Rn.
Mhm.
Locally
So
TM.
actually, right, it's Tu is Tm is what is called a vector bundle.
Yes.
So I don't want to get into the definition of vector bundle, but it's like this picture where you have a bunch of vector spaces stacked above a given topological space. So the topological space is called the base, and these vector spaces are called the fibers. And the union of all the fibers gives you a topological space called the total space of the bundle. So in our case, the total space of the bundle is the topological space Tm. All right.
Hmm.
And what Bappa is saying is, for a vector bundle, the important condition is that this total space should be locally trivial. That means if I take any point in the base, then there is a neighborhood of that point in the base, such that if I take the union of all the fibers in that base, so that would be my set Tu, then that part of the total space is a product of the base open set U with the fiber Rn. So locally, it's a product with a vector space, but not globally. So for example, the simplest example you've all seen of a vector bundle which is not a product is you take the Mobius strip. So that would be the circle, you take S1 cross the real line R. So here I have a copy of R for each point in S1. Okay. But I do something, what I do is, before I'm going to close up the circle, when I come to the near the end of the circle, then I glue these two fibers here by the linear map x goes to minus x. I glue these fibers this way, right? That's what you do when you take the Mobius strip, right? The Mobius strip looks like this. I can't draw it, but anyway, you understand what I mean, right?
Yes.
You know what a Mobius strip is, right?
Mhm.
So yeah, this is a bad drawing. You'll have to excuse me, but you know what it is. So yeah, so so this is it, right? Okay, let me try a better drawing. Let me see. I have to do some meditation and try and do a better drawing. Is this better or worse? Maybe this is better. Is this clear? Yes.
Yes. Yes. Yes, sir. Yeah.
So this is a vector bundle where the fibers are R, okay? But this is locally trivial. Locally, it looks like a product, but not globally. It is not globally trivial.
Sir,
Yes,
are there only two? I mean, up to isomorphism, are there on? Or, yeah.
yes, yes,
Two.
yes. There are only two rank 1 vector bundles on the circle.
Yes.
The Mobius strip and the product, the trivial bundle. Yeah, that's right. Yeah, that's right.
Sir,
Yes,
while defining the topology on TM,
yes,
you are actually identifying TU with open subsets of R2 and taking the topology from there, right?
correct, correct, correct.
How are you getting the second countability and Hausdorffness from that?
That comes from the second countability and Hausdorffness of M. So you can do that as a little exercise. M is second countable, right? So you have a countable basis for the topology of M,
Yes, sir.
right? So you have a countable collection of UIs, right, which cover M.
Yes.
Yes? And the UIs form a basis for the topology of M. Now you look at the TUIs, right? So each
Yes.
TUI is second countable, right? Is that clear? The TUI is homeomorphic to an open set in R2N, which is second countable. So you have a countable union of second countable subsets. So the whole space is second countable, right?
Yes, sir.
Right? Countable union of countably many sets is countable, right? So it's second countable. And for the Hausdorff, that's easy. If you take 2 points, so if they belong to different fibers, that means their foots they have different feet. So one belongs to TPM and the other belongs to TQM. Then you can take disjoint charts U and V around P and Q. So, so then your first tangent vector belongs to TU and the second tangent vector belongs to TV. And these are disjoint open sets. Okay, so that gives the Hausdorffness if the base points are different or the foot are different. And if they belong to the same tangent space, then you just look at this chart, TU, right? Then both belong to the same TPM. So they get mapped to some two different vectors in the same copy of Rn. So then I have 2 points in this, 2 distinct points in this open set in R2N that I can separate by 2 neighborhoods in R2N, right? By 2 disjoint neighborhoods in R2N. And then I pull them back to TU and I get 2 disjoint neighborhoods in TM. Is that clear?
Yes, sir.
Okay, so it's second countable and Hausdorff. Yeah. Any other questions? Okay, so so what is a vector field? You can, so what is a smooth vector field? So we said that a vector field was a map X from M to Tm, which is actually what's called a section of this vector bundle. What that means is for each point below in the base, you choose a vector in the fiber above, right? So for all P and M, XP is a point in the fiber TPM. Okay. And we said that X locally we can write as summation AI del del Xi. Right? Where AIs are functions. And so X is C infinity, we said. If and only if for all I, AI is C infinity. This was our definition. Okay, right? And this is the same thing as saying that X as a map from between manifolds M to Tm is a smooth map of smooth manifolds. Is this clear? Because what are these AIs? AI is nothing but it's the coefficient of del del xi in X. So AI is nothing but dxi applied to X, right? Yes?
Yes.
So AI is C infinity means that dxi of X is C infinity and dxi's are the local coordinates on Tm, right? So the AIs are the local coordinates of X. Is this clear? Right. So when is a map between manifolds? When its expression in the local coordinates is C infinity, right? And its expression in the local coordinates is just A1 to AN, which are the dxi's applied to X. Is this clear?
Yes.
Yes. Okay. Okay. So now I want to talk about the flow of a vector field. So how a vector field on a manifold gives rise to okay, all right. Okay, so before that, well, let me talk about something else, which is so okay, we're going to run out of time in 2 minutes, but let me just keep talking a little bit. Right. Okay. So if I have X is a C infinity vector field, it defines what's called a derivation X from. Okay, well, before doing this, let me just, what time is it? We have less than 1 minute. Okay, so let's just wait for this to finish. We'll join again and then I'll talk about the flow of a vector field and integral curves. So we'll join using the same link, right?
Yes. Sir.
Yes, yes.
Yeah, so I'll see you in about 2 minutes after this finishes. I'll see you in about 2 minutes. We can join again. Yeah.
Sir, we can do one thing. We can manually leave the meeting and we can join again.
I see. That should work, right?
Yes. Yes.